All right, where we left off on problem 4 was I was trying to simplify the first derivative, and it looks like it's going to be e, right? This actually is going to be 1, so equals e to the minus x over k, 1 plus 1, or 2 minus x over k, right? So that's what it looks like. Now, I said it equals 0. I like to look at it with that e in the bottom because it gets rid of the negative exponent. So notice that this is always positive. So therefore, we are going to look at this to find out the critical points, or the max and mins, right? 2 minus x over k equals 0. 2 equals x over k. Cross multiply 2k equals x. K equals, whoops, I'm sorry, I'm solving for x. That's what I need to solve for. Oh, I think I got it right there. So x equals 2k is where our critical point is, right? Now, we're looking at from 0 to infinity, right? At 2 over k, at 2k somewhere in here, we have a critical point. But I need to test the critical point and the end point here at 0 and end behavior. What's happening as x approaches infinity? So if I take the function at 2k, this first, let's see, at 2k, so it's 2k minus k, e to the minus 2k over k. Right, and that k's go away, so I end up with equals k e to the minus 2, which is really k over e squared. Positive, and k is positive. All right, let's test what's going over here. It's 0. It's going to be f of 0 is 0 minus k. E to the minus 0 over k, right? Which means e to the 0, which is 1, so it's negative k. F at 0 equals negative k. And let's see what happens as x gets really large. So the limit as x approaches infinity is going to look like, if we go back, it's x minus k over e to the x over k. Well, the denominator is exponentially approaching e to a really, really large number, right? And it's approaching way faster than this is approaching. So if the denominator is growing at a larger rate than the numerator, this is approaching 0. So what we have, if I go to the next page for a second, what we have is we found out that the function at 2k, which is somewhere in the middle of our domain, looks like this. The function at 0, which is the end of our domain on one side, and the limit of the function as x goes to infinity on the other side is 0. This is k e to the negative 2. So this really is k over e squared. Right? K is a positive constant. So this thing right here is positive, isn't it? This thing right here is negative. And the limit down here is 0. So we have the, just starting at 0, our curve's up here, it's coming down here. Oops, I'm doing the wrong way, sorry. At 0, it's negative. At 2k, it's positive. And as it approaches infinity, it's heading towards 0. That means our critical point is a maximum. Okay? So there is a global maximum at x equals 2k, and that f of that 2k, we said, equals k e to the minus 2. This thing's... Now, this thing's headed towards 0. This is a negative k. So our global minimum, right, on our interval, what's the lowest minimum we have a global minimum at f of 0, which equals negative k. Well, it's a lot of chitty-chatting there, but that's not a bad one. It's just, you just have to keep it straight, okay? It's good to remember when they say k is a positive constant, that helps us out. All right, so at noon, ship A, here's A, is 8 kilometers west of B, so this is 8. Ship A is sailing south at 4 kilometers per hour. That means A is traveling with respect to time 4 kilometers per hour. B is traveling north, and B's speed, right, the speed or the rate of change is a derivative. dB dt is 2. Now, let's define this as positive. So this 4 is in a negative direction, isn't it? So this one's changing 2 kilometers per hour. All right? It says, how fast is the distance between the ships changing at 1 p.m.? Well, at 1 p.m., ship A will be negative 4 south, kilometers south. Ship B will be 2 to the north. Now, I would like to know what D is right now. Its value at 1 o'clock. Well, basically what I can do is this. Here's the 8. If I took this 2 here and put it with, let's see if I moved, if I took 2 this way and 2 this way, so I ended up saying we're traveling at 6, that'll allow me to get the value of D. Okay, I just took the 2 up here and I shifted the line down 2 there and 2 there. Right, because this is a distance. Distance is always positive. So I'm going to do 36 plus 64 equals 100. So the value of D at this point is 10. D is 10, but what we want is how is the derivative changing with respect to time? All right. So our diagonal looks like this. If this whole thing is 8, right? Then I'm going to call this portion of it x, and I'm going to call this portion of it 8 minus x. So let's say, and I'm going to treat these diagonals as the first diagonal plus the second. So the entire diagonal is this one, which is 4 squared plus x squared. The second diagonal here is 2 squared plus 8 minus x squared. Okay, so let's FOIL this. 64 minus 8x means minus 16x plus x squared. That's a plus x squared, isn't it? Oh, I think what I'm going to do instead is take the derivative first. I don't want to worry about that. Okay. If instead I'm going to take all of this. Oh, I know what it is. We're going to, instead of putting the numbers in, we're going to say y1 and y2, where y1 is this, y2 is this. It's going to help us as we take the derivative, because we need to be able to use the change in y. All right, so, and this is really d squared, isn't it? All right, so d squared derivative equals 2d dt that equals 2y1 dy1 dt plus 2x dx dt plus 2y2 dy2 dt plus 2, 8 minus x times a negative 1 for the inside, d x dt.